Hello and welcome to the course of Heat Engineering. This is lecture 3. In this lecture, we will learn about the plane heat transfer from a plane wall by using the electrical analogy of heat transfer. So there exists between an analogy of heat flow and electricity flow. So what is electricity or current? It is basically a rate of flow of charges and which is resisted by the property of the conducting material, which is known as electrical resistance, and the cause of that flow of charges is potential difference. So in a similar manner, we can say that the cause of heat transfer is the temperature difference T1 T2. If T1 is greater than T2, then the heat flow will be from T1 to T2, and there will be a resistance because of the property of material that is called as thermal conductivity. So we will apply the this analogy. If we use Ohm's law, V is equal to IR, we can replace V with the temperature difference, and we can replace the current with heat transfer rate. So rest of the term will be equivalent to the heat transfer resistance. So in case there is a summary of electrical analogy. So if the I is the current in electrical system and R is the resistance and del V is the potential difference. So in heat transfer, the in Cartesian conduction, the heat transfer current will be analogous to Q, and the resistance, which is known as thermal resistance, will be given by L by Ka, and the potential difference, which is responsible for the heat flow, will be del T. So in case of cylindrical conduction, this becomes ln R2 by R1 upon 2 pi Kl, where R1 R2 is the radius of that shell. So similarly, we can derive the formulas for the thermal resistance for different setup. So in case of convection, we can also arrive at a quantity 1 by HA, which can be equivalent to the convective resistance. So let us take a one-dimensional steady state heat conduction through a slab. So because it is a one-dimensional and steady state, so there will be no term of which relates temperature to the time, and assuming that there is no internal heat generation and the properties are constant, so our the heat conduction equation reduces to this del 2 by del x2. So upon integrating twice, we can obtain the temperature distribution in terms of x, and the boundary conditions will be the at x equal to 0 temperature is T1, and at x equal to L temperature is T2. So using these two boundary conditions, we can solve or obtain a relation of temperature variation along the x direction. So heat transfer can be given by Q is equal to minus Ka del T by del X, and from this we can see that if this Q is I and this T1 minus T2 is del V potential difference, then rest of the term is 1 by R. So R here is thermal resistance, which is L by Ka. So in case of a steady state one-dimensional heat conduction with heat generation, we will get this governing equation, and similarly we will solve it by integrating twice with respect to x, There will be two constant of integration which will be obtained by applying the boundary condition which we know at x equal to 0 and at x equal to L. So we can get the temperature variation with respect to x, and we can plot this. So because of the symmetry, we will get that because the heat generation is uniform. So and at the symmetry line, we will get the maximum temperature. So let us take another example of cylindrical coordinate system in which there is a hollow cylinder, and we want to know the temperature distribution of this hollow cylinder. So mathematical formulation for this from the fundamental equation of conduction, and because there is no heat generation, we will get in Cartesian polar coordinate the heat governing equation as d by dr of r dt by dr, where T is the temperature variation in the radial direction, right? And the R varies from A to B, where R is the radius, so internal radius is A and external radius is. So similarly, solving again by differentiating by integrating twice with respect to R, we will get the radial temperature difference distribution as this. So using the boundary condition, we will get the value of C1 and C2. The boundary condition are known at R equal to N or R equal to B. So the formula for the temperature distribution will become like this. And if we want to calculate the heat flow, then we can calculate the heat flow from like this. And since the d by dt of d by dt by dr is 1 by rc1, so q becomes 2 pi kl upon ln b by a t1 minus t2, where b is outer radius and a is inner radius. So rearranging, we will get the thermal resistance because we can assume by electrical analogy this is I, this is del V, and rest of the term is 1 by R. So in this manner we can calculate the equivalent thermal resistance of any system in which the steady state heat transfer is conducting. Let us calculate the thermal resistance of a hollow cylinder. So if we take a hollow cylinder whose inner and outer radius are R1 and R2, the temperature at the inner radius at a distance R1 is T1 and the outside temperature at the distance R2 is T2. And suppose the Q dot is the heat flux conducting through this slab. So using Fourier's transform law in radial coordinate system, we can write the conducting heat transfer rate as minus Ka dt by dr, where A is the parametric area which is normal to the heat transfer direction. So rearranging the terms and integrating with respect to dr, the integrating limit will be R1 and R2, and where the temperatures varies between T1 and T2. So we can calculate the Q conducting cylinder as 2 pi KL T1 minus T2 over log R2 by R1. And we can write this equation in a typical analogy, electrical analogy form. Q is equal to del T upon R, where R is the thermal resistance of the cylinder. If we compare both these equations, what will be the value of R? We can get ln R2 by R1 over 2 pi KL. So now take another example of a solid cylinder with heat generation. So the governing equation of a solid cylinder with heat generation rate G naught will be this in cylindrical coordinate system, where at R equal to 0 we can assume that dt by dr is 0, and at outer radius R equal to P the temperature is known. So integrating twice we will get this, and applying the two boundary condition and putting the values of C1 and C2 back to the equation, we will get the radial temperature distribution with the heat generation like this. And we can calculate the heat transfer rate now by using the Fourier's law of heat transfer in radial coordinate system minus k dt by dr, and which will come this. And from this equation we can easily calculate the thermal resistance of this solid cylinder with heat generation. So now let us take another hollow sphere so that we can be comfortable of calculating thermal resistance in spherical coordinate system. So there is a hollow sphere whose radius are known, and the temperature at the inside and outside of that hollow cylinder is known. So without heat generation and steady state, the governing equation will be this, and we will integrate this twice and we will get this temperature distribution with respect to R. And using the boundary condition at R equal to N, R equal to B, we can calculate the constant C1 and C2. So putting back the value of C1 and C2, we will get the temperature distribution in this form. And now we can calculate the heat transfer for this hollow sphere. So once we have calculated the expression for the heat flow rate, we can use a typical tool of electrical analogy, and where the heat transfer is proportional to the temperature difference, and the rest of the term which are occurring is thermal resistance. So in this way we can calculate the thermal resistance of a hollow sphere. Now let us take some simple and composite system in a rectangular system. Suppose there is a furnace, and just outside of the furnace there is a refractory lining 1 and 2. Then there is a brick wall, and then there is the ambient. So the furnace is very hot and we want to calculate what resistance this composite furnace wall offers. So there are, suppose the length of each of those refractory lines 1 and 2 and brick are same, which has thermal conductivity K1, K2 and K3, and the temperatures are known, for example. So this can be analogized as a heat transfer through the slabs in series. So the thermal resistance of all these systems can be calculated, and Ra and Rb are the thermal resistance due to convection, and R1, R2, R3 are the thermal resistance due to conduction. So the total thermal resistance we can calculate as the sum of all these thermal resistance and we know that RA will be 1 over HA, where H is the heat transfer coefficient at the left side, and RB will be 1 over HA, where the H will be the heat transfer coefficient at the right side. So R1, R2, R3 can be calculated in a typical way of L by Ka, and once we get the total thermal resistance, we can calculate the total heat transfer rate. So let us take another system in which the temperature at the left and right side is T1 and T2, and the system is insulated at the top and bottom, so that the heat transfer is only one direction, and the slabs have different thermal conductivity. So is the case, so their resistance, thermal resistance will be different. So this system can be transferred into an electrical network where RB, RC and RD will be in parallel because they experience the same temperature difference. So by calculating the equivalent thermal resistance of the system, we can calculate the total heat transfer rate through the system. So as we know that the temperature at the left and right side is known.